Alright.
My form just got worse and worse.
We kind of rushed this one at the end because the bell's going to ring, so let's pick it up here again.
Okay.
We're doing the circumscribed rectangle. That means that part of each rectangle is outside of the function. Okay, I need you guys eyeballs on the screen up here. The area of all 5 of those rectangles added together is going to be greater than the actual area underneath the curve. Yes?
Yeah.
Okay. That's what happens with circumscribed rectangles. In a second here, we're going to do the inscribed ones. Those are the ones where all the rectangles are inside the curve. That area is going to be less than the area of the curve. So the actual area of the curve is in between the inscribed area and the circumscribed area. Okay. Oh, we already did? No, we didn't.
What did we do inscribed?
We did inscribe.
See?
We didn't actually find the area though.
Oh, we didn't?
I messed up inscribed.
We were finding the area of the circumscribed. So let's just quickly review because it's been a long dang weekend. Yeah.
When you're inside the curve, and these ones are when you take it outside.
You could get a lot closer to the approximation. Yeah. You guys ready? Should I just wait for you? Okay. We're adding 5 rectangles. Okay? But if it's a circumscribed, the part of each rectangle that's actually on the function is the left side. You guys follow?
Yeah.
So if you see where my pen is pointing on the screen right here, what's the value right there for I?
1.
Or along this axis, what's the value right here along that axis?
0.
It's 0. Right? The value right here on the left side of this rectangle is 1. The value right here,
2.
3, and 4. But since there's 5 regions, but each time we're plugging in 1 less in that region, that's why we had to use I minus 1. You guys remember that?
Yes.
Okay. The width of each rectangle is 2/5. The entire length of the interval was from 0 to 2, but since we're breaking it up into 5 equal intervals, each length was 2/5. Remember that? Or each width, rather, was 2/5.
Yeah.
Is this ringing a bell now?
Yeah.
The actual height of each of these rectangles, if we're talking about the left side, since the left side of each rectangle is on a function, it's a function value. That's why we have f of this. Okay? The function itself was somewhere around here. Where was the function? Somewhere around here. Oh, here it is. Negative x squared plus 5. That was the actual function. Okay. Now, if we're evaluating a function, don't we have to have something to plug into the function?
Yeah.
Okay. Now, that's where this is. This is the input into each function. What's the first input that we're going to plug into the function? What's this quote-unquote x value right here? 0, right?
0.
So, but we're using still I equals 1, 2, 3, 4, and 5. Since there's 5 subintervals, we start with I equals 1, I equals 2. That's why we have to have an I minus 1. That's going to turn the input into 0. Shouldn't the first input be 0?
Yeah.
Okay. Now, this 2/5 happens because each interval is just a multiple of 2/5, because each width is 2/5, right?
Yeah.
You guys following? So the next interval would be 4/5, 6/5, and what is that? 8/5. Those are all of our inputs we're plugging into the function. Yeah.
So why do you have to put that in the second
Plug.
the 2/5 for the height?
Because this each x value is either 2/5, 4/5, 6/5, or 8/5. You looking where my pen is right here on the screen? This is 2/5, 4/5. Because it's increasing at a regular interval, we can just do that using this summation idea. When I equals 1, we get 2/5. When I equals 2, we get 4/5, and then 6/5 and 8/5. Okay? I suppose it could be done either other ways, but where this is eventually leading, I showed you a picture last time. What if we increase this to 8 rectangles? Wouldn't that give us a better approximation? What if it was 100 rectangles?
Yeah.
Eventually we're going to increase this to infinitely many rectangles, so we're going to have to take a limit. And so it's better to use this idea of having subintervals of I when we're taking a limit to infinity. So this is where we were when the bell was ringing. These right here, you guys, these were the values that we got when we plugged into the function. Okay, what were these? Okay, I kind of squoze this in right as the bell was ringing, so you might have missed it. Each of these values is a height, isn't it? You guys with me here?
Yeah.
These are a height of a rectangle because these came from the function itself. And isn't each height of a rectangle on the function?
Yeah.
So then what are these? These are the width. Why do we need a height and a width?
Area.
Because we want an area. And how many rectangles are there?
5.
That's why there's 5 different pieces here. Okay, if we add up all 5 of these values, we should approximate the area under the curve. Okay? So I asked you to try it at home. You might not have had time, but do it now. Okay? Add these up. Probably my fault. You're going to have to go through that process again. This is wrong. That number's wrong.
Wait, what?
This number right here is wrong.
How is it wrong?
Dang it. How did we not see this? Check this out. Zane suck. We're using I equals 1, right? What's 2 times 1? 2 minus 2? 0 divided by 5. So our input into the f function is what? 0. So here's the f function. 0 squared. 0 squared is 0 times negative is still 0. 0 plus 5?
5.
So that should actually be just 5. I don't know where that came. I don't know where
Because
that.
you have to multiply it by 2/5 and then it turns into 2.
Yeah.
The inside times the 2/5.
And then you don't multiply it.
Well, yeah, we still need the height. We still need the height. This is the height, and this is
Oh, the 2/5 in front of
the 2/5 is the width. So what's 2/5 times 5? 2. So that should just be a 2.
But isn't the function for height, it's the function of 2/5? Oh wait, never mind then, it's 0. Oh my gosh.
So let's try to do the computation real quick one more time. What'd you get, Diana? Anybody else get that? With the new and improved height?
200. So would it be 200 over 125? No, not 200.
So, just before we move on, this is an approximate area, yes? Greater than or equal to or less than the actual area. Greater than because these are circumscribed rectangles. Okay? If we wanted a better approximation, would an inscribed area be a better approximation? What do you? What would be a better approximation? More rectangles. Okay? The more rectangles we could add to this. Now, just by hand, more rectangles would give you a better approximation, but the flip side to that is by hand, it would be kind of crappy. But anyway, let's go more general. General, upper, and lower sums. I think I mentioned this briefly last time. An upper sum, that would be circumscribed. A lower sum would be inscribed. They're called upper and lower sums because the upper is a little bit greater than the actual area. A lower sum is the inscribed. That's going to be a little bit lower or less than the actual area. So put a graph on your paper. We're going to do a real easy function to begin with. F of x equals x squared. Just the right side of it. We're going to do the general lower sum first. So find the lower sum between 0 and 2. What we're going to be doing here, though, is an arbitrary amount of rectangles. It doesn't specify a number of rectangles, so we're just going to keep it in general. The number of rectangles is going to be n. Okay. Let's actually specify that using n rectangles. So instead of a specific amount, find the lower sum between 0 and 2 using n rectangles.
It's under the curve, right?
Yeah, inscribed under the curve. Now, you guys really got to think through this. So turn your brains on here. The last example we did, we were going still between 0 and 2, right? How many rectangles were there? So then what was the width of each interval? If we're going from 0 to 2 and there were 5 rectangles, what was the width of each interval? Okay. So in this case, we're going between 0 and 2 and there's n rectangles. So it's going to be 2 over n, right? In general, okay, the width of each sub-interval, we're going to call that delta x, is equal to b minus a over n. b minus a over n, where b is the, in this case 2, that's where we end. Where does the interval start? 0, so that'll be a. A is 0, b is 2. So 2 minus 0 is 2. So for our case, you guys are right. It's going to be 2 over n. Okay. So let's just put some rectangles on here. Now, I'm going to use a specific amount, but just to illustrate a point of what the rectangles look like. Now, if they're inscribed, at the very top, which side of the rectangle is going to be actually touching this function, the right side or the left side? Think about this for a second. So before I draw this, if this is going to be inscribed, doesn't it have to be the left side? Which one is actually touching the function? Does that make sense what I'm asking now? So just draw a couple of rectangles. Make sure, ooh, that was not good. Make sure they're all same width. Yo.
What's B and A? What are those things?
Well, in this case, A is where the interval starts, 0. B is where the interval ends along the x-axis. Is that what you're asking? Okay. You okay with this? Now here's 2 right here. Here's where our interval is. Let me go back to this last example that we just did here. In your notes, take a look at this example in your notes, you guys. The circumscribed one that we did. Wasn't the left side of each of these rectangles also on the function? If it's the left side of each rectangle that's on the function, we had to have this I minus 1. Because if we're starting on the left side of each rectangle, the very first value we're going to use as an input is 0, because we're on the left side. Remember that? So, left side endpoint. This is a left side endpoint. Means that each input is going to be 2 over n times I minus 1. Well, let me just make sure we're clear. Why I minus 1? It's a left-sided endpoint. If it was a right-sided endpoint, it would just be, we'll do that in a second. If it's a right-sided endpoint, it's just I. If it's a left side, it's I minus 1, so we can start at 0.
What is the B and the A stand for again?
The B and the A is where the interval is along the x-axis. And what was this again? 2 over n? That's the width of each subinterval. Now what happens when I equals 1? We're going to get 0, which makes sense. That's the left side of our first rectangle. That should be right along the y-axis if we're starting at 0. Alright? You with me still? Left side of each endpoint means we're going to be 2 over n times I minus 1. Now look back at our last example. What did we do with this value? In this case, it was 2/5 times I minus 1. What did we do with that value? We plugged it into the function to find the height of each rectangle, right? We multiplied each height by the width, because a height and a width makes an area. How many rectangles? In that case, it was 5. In this case, it's n number of rectangles. Okay? So, I'm out of room. Well, lesson's over. I'm out of room. Shoot. All right, hold on. We can fix it. No, we can fix this. Check this out. New page. Come on. There it is. In this particular unit, I'd have to go count. I can't remember off the top of my head. We have a few. Okay. So here we go. Using left endpoints, the lower sum we're going to use sigma notation. Now in the last example, we started from I equals 1 and we ended at 5 because there were 5 rectangles. How many rectangles here? N, so we're going from 1 to n. Whoop, that's not a good. There's a better n. Okay. Refer back up in your notes to the previous example. What were we taking after we had the sigma? Didn't we have the width? Look at your example there. What was the width in this case now? So we're going to have 2 over n. Now we have to multiply that by an actual function value. So that's going to be f. And what is f in this case? In this case, f is x squared. Our input was this value right here, 2 over n times I minus 1. Okay. Put this whole thing in brackets so you remember that this whole thing, we're taking the sum of that whole thing. Alright, see if you can follow this. What happened there? What is the function? The function is x squared, right? It's a pretty simple function. All you do is take the input and square it. Isn't that what it means to do? X squared, take the input and square it. What's the input? 2 times I minus 1 over n, that's the input. And according to the function, what should happen to the input? It should be squared. So that's all we've done here is we've squared the input. Now we don't have function notation anymore. You guys realize there's no more f because we evaluated the function now? You guys okay with that? Okay. Let's do one more. I'm going to kind of go out on a little bit of a stretch here. There were a lot of steps that were skipped in there, but what is that? There were a lot of steps that were skipped, but do you see, can you maybe see where this might have come from? All right, we don't have time to go through all the steps, but let's quickly go through some. What happens when you square a fraction? Isn't this a fraction being squared? When you square a fraction, what happens? You square the top and the bottom, yes? So wouldn't this eventually be an n squared? And then you multiply that by another n, so you get, do you see where that n cubed came from? Now if we're squaring the top, eventually at some point, aren't we going to have a 2 squared in there, which is 4, and then 4 times 2 is, you see where the 8 might have come from? Okay, so all I did is factored out an 8 over n cubed, and that left us with this quadratic I squared minus 2i plus I. That would have come from just squaring I minus 1, isn't it? I minus 1 squared is I squared minus 2i. You see where that came from now?
Yeah.
Okay. Now, notice on this summation, we're only plugging in values into I. Isn't that correct? You guys understand what I'm saying? So what about 8 over n cubed? Is that, are we ever going to plug anything in for n? Ever? You guys understand what I'm asking? According to how this is set up, aren't we only going to plug things in for I?
Yeah.
So that 8 over n cubed can actually come out of the summation process because we're only ever going to plug things in for I. So take out the 8 over n cubed. Now I want you to write it like this. From I equals 1 to n of I squared minus 2, and then another summation. Do you see what I'm doing here? I know I'm writing kind of fast, but yeah, I took out the 8 over n cubed out of the summation process, and now we're taking the sum of a polynomial. That means you can split this up into, in this case, 3 different sums.
Whoa. But you can do that?
Yep. Okay. I know this is like a lot of generalizations, not a lot of specifics, but are you okay up until this point? Look through your notes right at the very beginning. Did you write, I hope you wrote this down, but did you write something down regarding the sum of I squared? I gave you a little formula. Look in your notes. There should be a formula when you're trying to evaluate the sum of I squared.
Oh, yeah.
And then wasn't there a formula for taking the sum of I? So let's use the formulas. Oh, regarding this last one here. Isn't there also a formula when you're taking the sum of a constant?
Yeah.
It's n times c, where c is the constant. So in this case, that's just going to turn into n. So all of these can be changed into a formula, couldn't it? So let's change all of those into their formulas. So we have 8 over n cubed, and now we change all of these into a funky formula here. So the first formula is n times n plus 1 times 2n plus 1 all over 6. Then we subtract 2 times another formula, n times n plus 1 all over 2. What did we decide this last summation was going to become? Just 1n, or just n. This next part, for sake of time, I think would be best if you just not trust me. It's just, couldn't we eventually combine all these, expand it all out, and write it as a polynomial? It would take some doing, okay? But this is what it would simplify to. Trust me, there is a point. The point is not just mindless exercising. There is a point here. I'm going to show you this in just a second. We had to simplify this. This is not something you're going to have to reproduce on your own. Okay? This process I'm showing you is not something you're going to ever have to do on your own. Okay, but I just wanted you to know where it came from. If we distributed now into the parenthesis, what would we get? This you can do. This next part you can do. Pretty quick, actually. 8 over 3 minus 4 over, let's see, 4 over n plus 4 over 3n squared. Whew. I know it's been a long process, so you might have lost sight of what we were even doing. What were we even trying to find in the first place? Which sum? It was a specific sum, the upper or the lower? This is lower sum. Now, didn't we decide that the lower sum is always slightly less than the actual area?
Yeah.
But how can we get a better approximation of the actual area? Well, I guess we could find the upper sum and seeing kind of where the middle of that is. That's true. But what if we increase the number of rectangles? What is n? Yeah, here's the point of all that, you guys. So don't miss this. What was n?
The number of rectangles.
The number of rectangles. So if I let n equal 3 for 3 rectangles, is the lower sum going to be a very good approximation of the area? How many rectangles should we use? So what if we now took this lower sum and did a limit as n approaches infinity? Okay.
We're gonna use logarithms next.
Not next, but soon.
Oh my god. It's like,
Okay.
it's like
This-
a plot twist.
This limit you guys can actually do. This isn't that hard. There's nothing to plug into here, so that just stays in 8 over n. What happens to 4 over n if n approaches infinity? You guys know this. The value gets smaller and smaller and smaller and smaller until eventually it's 0. What about 4 over 3n squared if n approaches infinity? That goes to 0.
Let me just understand better.
So what are we left with?
No.
The limit as n approaches infinity equals 8/3. Okay? You guys, this is the actual area. Actual area
Yeah.
under f of x equals x squared between 0 and 2. Yeah. Now let me relate this to something. You guys remember the very first week, maybe the second week, we learned how to find a derivative using a limit? Remember how you had to do the f of x plus delta x minus f of x all over delta x, and the limit approached 0?
Yeah.
Before I taught you the real way to find derivatives, that was the only way we could find a derivative. You remember how you hated that process?
Yeah.
Wasn't there a much easier way? Well, this is the same thing. This is one way to find the area under a curve. Is it a nice, pleasant way?
No.
No. There's an easier way. Okay? But in AP Calc, you can't just jump to all the shortcuts. You have to understand where it came from. Where does the area come from? It's a limit of an infinite number of rectangles under a curve. Okay? You remember what we learned not last time, but the time before that? Antiderivatives? Okay? That's all finding the area under a curve really is finding an antiderivative and then plugging in 2 values into that antiderivative. What do you think? In this case, what would the 2 values of x be that we would plug into an antiderivative? y0 and 2? That's the boundary of our integration between 0 and 2. So the actual process that we're going to use most often isn't very hard. You take an antiderivative, you plug in a couple of x values. Okay? That's going to equal what we got here. And the point of this was to show you where that process came from. I know it's not super easy. It's not a short process either. Okay? But let's formalize this. Definition of the area under curve. Under a curve. There we go. So let f, it's got to be a continuous function. There's not any gaps or jumps or vertical asymptotes. So let f be continuous and non-negative. On the interval AB. The area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a. And x equals b. Let's just draw a quick picture so you understand what this is even talking about. So we're trying to find this area, right? So here we have the function f. We have two vertical lines between a and b, x equals a, x equals b. So we're trying to find the region bounded by the graph, the x-axis, and those two vertical lines. That's all that's saying. You with me now? Okay. The area is a limit as n approaches infinity of the sum, just like we did in this last problem, from I to n, from I equals 1 to n. So on your picture, I had this little rectangle here where I'm drawing it. So if the function is f, or if the function is f, and this right here is ci, right in the middle of that rectangle, then the height of that rectangle is f of ci. So that's what this means right here, f of ci. That's just the height of each rectangle. Delta x, that's the width of each subinterval. That's b minus a over n. So the width of this rectangle is delta x. We have a height times the width. That's just going to be the area of each rectangle. There's an infinite number of rectangles because n is approaching infinity. That's the definition of the area under a curve. Does it have to be found using the limit definition? No, it doesn't have to be. Just like the derivative doesn't have to be found using the limit definition. This is one way to do it. It's the longest way possible, but it's a way to do it.
Works.
Okay. So this is what you can expect to see on your homework. Find the area. The region bounded by f of x equals x to the third. The x-axis between x equals 0 and 1. Using the limit definition Oh, by the way, before I forget, turn on your graphing calculators. I hope so. Yep. Turn on your graphing calculator. Let me show you something kind of cool on your graphing calculator.
You can just plug in the equation and it'll solve it for you.
Maybe.
Yes. Yes. I was waiting for the day you would teach us this.
Turn on your graphing calculator.
I never have to pay attention. I just have to remember the calculator stuff.
Unless this is on the no calculator part.
Yeah.
Well, that part's on.
So go into y equals, type in the function, in this case, what was it, x to the third, so type in x to the third. I'm going to change the window, because we're only going between 0 and 1, aren't we? So I'm going to change the window so we have a better look at what this, I'm going to put the x max at 0, or the x min at 0. X max, I'm going to put that to 3. And then from 0 to 10. Pretty much I just want to see the function in the first quadrant. You guys with me? Now I'm trying to find the area between what two x values? 0 and...
And 2, 1.
Is it 0 and...
0, 1.
Yeah, 0 and 1. Okay? So hit the second button and trace. It's been so long since I've done this. Hold on now.
That's 7.
We're finding essentially the area under a curve. Didn't I explain that a few moments ago as an antiderivative?
Yeah.
What's another way of saying antiderivative?
Integral.
Integral. Do you see an option on there
7.
that has integral? So scroll down there. Oh, come on. So it asks for a lower limit. What's our lower limit? That's an x value. Our lower limit is the smallest. We're going between 0 and 1, right? So the lower limit is 0. Upper limit then would be the right side. So this would be 1. You guys with me on this?
How do you change the sign?
Just type them in.
Oh, I never knew that.
No way.
It's kind of hard to see on my screen, but maybe it's a little bit easier to see on yours. Does this tell you what it is?
Oh my goodness,
It's 0.25.
0.25? Which is 1/4?
Yeah.
Okay. Doesn't it even shade it in on your calculator?
Yeah, it does.
Cool.
Dude, whoever made these calculators was a genius.
Anyway, I just didn't want to forget.
Genius. Straight up. It's like, there's no one in the world. How do you program?
Here's how it would have to be shown if this were a test question. You ready?
I'm never going to do my work again.
Area is equal to the limit from I equals 1 to n of f of ci times delta. Isn't that the isn't that the definition that we talked about?
Yes.
Okay, we gotta think real careful about this. Delta x was the width of each subinterval. If we're doing n the number of rectangles, what's the width? Think about the last problem. We were going from 0 to 2, and we were doing n number of subintervals, so what was the width of each one? 2 over n, right? Now we're going from 0 to 1, and we're doing n number of rectangles, so the width is 1 over n. Okay. You guys okay with that? Yeah, that's the width of each rectangle. Because the width is along the x-axis. So if you're changing along the x-axis, that's a change of x or delta x. Does that make sense? Okay, now this one here, that's going to be our height. Now, to save time, I only showed you last time the lower bound. The upper bound, if we took the limit, I need you guys to pay attention to this for a second. Whether we use the lower bound or an upper bound, if we use an infinite number of rectangles, isn't that going to equal the actual area?
Yes.
So in the last example, the one that took like 20 minutes, I did it with a lower bound. The lower bound had to use I minus 1 because the left side of each rectangle was on the function.
Yes.
You guys following? But we could have very well used the upper bound and used the right side. If we're using the right side of each, I'm talking about the very top of each rectangle, we don't have to use I minus 1, we just use I. You guys with me on that? So it would have been maybe easier just to use I instead of I minus 1, but I don't know. So in this case, what's the function?
Function of x equals...
The function is
x equals x cubed.
x cubed. Okay. Our input is going to be our width multiplied by I. So our input is just going to be I over n. Last time our input was I minus 1 multiplied by each subinterval width. But this time it's just I because we're doing a right side or an upper sum. Now what happens if I put an input of I over n into our function? What's the function? So if I put I over n into the function, isn't that just going to be cubed? So what this turns out to be is the limit as n approaches infinity of our sum from I equals 1 to n which is f of I over n, right? But if I over n goes inside of f, isn't it just going to turn out to be I over n to the third power?
Oh, yeah.
And that's going to be multiplied by 1 over n.
Okay.
I'm going to go out on a limb here and assume that you can follow me on this one. You ready? Oops. I to the third over n to the 4th. You with me on that one? Did I lose anybody? Where'd the n to the 4th come from? N cubed times n, right? Thank you. He's not here. And this is just like I tried to explain on the last example. We're plugging things into I, not n. N doesn't need to be part of this summation process then. What do we do with it? Then we take it out of the summation? Okay. So if we take out the let me just write this. N approaches infinity of 1 over n to the 4th. If we take out the 1 over n to the 4th, aren't we just left with I to the 3rd? So check back in your notes. I thought we had a formula for the sum of I to the 3rd. There was one in there, right? So now we replace the summation with its formula. So it's the limit as n approaches infinity of 1 over n to the 4th. Now we replace that summation with, what was it, n squared times n plus 1 squared over 4. Now, this arithmetic isn't super tricky. N plus 1 squared, isn't that just n squared plus 2n plus 1? And if you multiply that with another n squared, you're going to get n 4th plus 2n to the 3rd plus n squared. Okay. Rather than dividing the whole thing by 4, let's divide each one individually. So this is going to be 1 over n to the 4th times n to the 4th over 4 plus n to the 3rd over 2 plus n squared over 4. You alright with that? We already know what the answer is going to be, don't we, by the way?
Yes.
It's going to be 1/4?
Yes.
Okay, so just make sure we know that the answer should be 1/4. Do you see where that might come from now? What if we multiply this 1 over n to the 4th into this parenthesis now? You guys can do this, come on.
So you times that be
For the first terms, wouldn't the end of the 4ths cancel out?
yeah.
So that's just 1/4.
And then just be 2n 1 over 2n
Plus 1 over 2n
plus 1 over 4n squared.
plus 1 over 4n squared. And we're taking the limit of that as n approaches infinity. I know this seems awful. It is awful. for this section. It's not out. Finding the area under a curve is actually pretty easy. Not using this way.
And using the easy way.
But if the limit approaches infinity, that goes to 0. That goes to 0. And we're left with 1/4, 0.25. Okay. So we have a few extra minutes, so I'm just going to do a couple homework problems with you guys. That's the end of the lesson.